What if you could soar through the cosmos and visit every single moon in our solar system in one incredible journey? Picture yourself gliding past worlds of ice and fire, ancient craters and active volcanoes, methane lakes and diamond rain. Tonight, we're embarking on the ultimate celestial road trip, flying through every moon that orbits every planet from Mercury all the way out to the edge of our solar system. This isn't just about our familiar moon hanging in Earth's sky. We're talking about over 200 moons scattered throughout our solar system. Worlds so alien and extraordinary that they challenge everything we thought we knew about what a moon could be. Some are larger than planets. Others are smaller than cities. Some harbour vast oceans beneath frozen shells. Others are shaped like potatoes tumbling through space. By the end of this cosmic voyage, you'll understand why some of these moons might be the most likely places to find life beyond Earth. You'll discover moons with atmospheres thicker than our own planets, moons that rain liquid methane, and moons so volcanically active they're literally turning themselves inside out. But here's what makes this journey truly extraordinary. We're not just going to list these worlds, we're going to fly through them, experiencing each one as if you were piloting a spacecraft on the adventure of a lifetime. What you're about to experience is a journey that no human has ever taken, but one that reveals the breathtaking diversity and wonder hiding in our cosmic neighborhood. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Let's start. Let's begin our journey where it all started, with the inner solar system, where moons are surprisingly rare. Mercury and Venus, those scorching worlds closest to the Sun, have no moons at all. They're cosmic loners, perhaps too close to our star's gravitational influence to capture and hold on to any companions. But as we venture outward, everything changes. Our first stop brings us to the most familiar moon in the entire solar system. Earth's moon, that silvery sentinel that has watched over our planet for over 4 billion years. As we approach, notice how surprisingly large it appears compared to Earth itself. Our moon is actually the 5th largest moon in the entire solar system, and proportionally, it's the largest moon relative to its parent planet anywhere we know of. Flying low over the lunar surface, we pass over the Sea of Tranquility, where human footprints still mark the ancient dust. The moon's face tells the story of our entire solar system's violent youth. Every crater we see represents an ancient impact, a cosmic collision from the time when planets were still forming and space was filled with debris. The largest impact basins, like the South Pole Aitken Basin, are scars from collisions so massive they nearly shattered the moon entirely. But here's something remarkable about our moon that makes it unique among all the worlds we'll visit. It's slowly spiraling away from Earth, moving about 4 centimeters farther out each year. Billions of years ago, the moon loomed much larger in Earth's sky, and the tides it created were hundreds of times more powerful than today. This gravitational dance between Earth and moon has shaped both worlds in profound ways, stabilizing Earth's rotation and possibly making complex life on our planet possible. As we leave Earth's gravitational embrace and venture toward Mars, we encounter our first truly alien moons. Mars hosts 2 tiny, irregularly shaped companions that look nothing like Earth's majestic moon. Phobos and Deimos, named after the Greek gods of fear and dread, are probably captured asteroids, potato-shaped rocks tumbling through space. Approaching Phobos first, we notice something unsettling about this moon. It's doomed. Phobos orbits so close to Mars that gravitational forces are slowly tearing it apart. In perhaps 50 crash into the million years, it will either Martian surface or break apart into a ring system around the red planet. Flying just above its cratered surface, we can see the grooves and fractures that hint at its eventual destruction. This moon is only about 22 kilometers across at its widest point, small enough that you could drive around its equator in a few hours. Deimos presents a different story. This outer moon of Mars is slowly spiraling away from its planet, just like Earth's moon, but much more gradually. It's even smaller than Phobos, a dark, coal-black world covered in a fine layer of dust that may have accumulated over millions of years. From Deimos, Mars would appear as a large, rust-colored disk in the sky. But the view would be relatively stable since this moon is tidally locked, always showing the same face to its planet. Now our journey takes us to where things become truly spectacular. Beyond Mars lies the asteroid belt, and beyond that, the realm of the gas giants, where moons exist in numbers that boggle the mind. Jupiter alone has at least 95 known moons, and new ones are discovered regularly as our telescopes become more powerful. As we approach the Jovian system, Jupiter's immense gravitational field begins to influence our trajectory. This giant planet, with more mass than all other planets combined, has created its own miniature solar system of moons. The four largest, discovered by Galileo over 400 years ago, are worlds unto themselves, each unique and fascinating in its own way. Io appears first as we enter Jupiter's domain, a yellow and orange world that immediately captures our attention. This moon is the most volcanically active body in the entire solar system, with over 400 active volcanoes constantly reshaping its surface. As we fly through Io's thin atmosphere, we witness something no human has ever seen directly. Massive volcanic plumes erupting hundreds of kilometers into space, painting the moon's surface in brilliant yellows, oranges and reds from sulfur compounds. The reason for Io's incredible volcanic activity becomes clear as we observe its orbital dance with Jupiter and the other Galilean moons. Io is caught in a gravitational tug-of-war, stretched and squeezed like a rubber ball, as it orbits Jupiter, while also being influenced by Europa and Ganymede. This constant flexing generates enormous heat within Io's interior, keeping it molten and driving the most spectacular volcanic display in the solar system. Flying low over Io's surface, we pass over volcanic mountains that dwarf anything on Earth, some reaching heights of 17 kilometers. The surface beneath us is constantly changing, renewed by volcanic activity so rapid that the entire moon resurfaces itself every few million years. No impact craters mar Io's face, because they're quickly covered by fresh volcanic deposits. Our next destination, a completely Europa, presents a different world. As we approach this ice-covered moon, its surface appears smooth and bright, reflecting sunlight like a cosmic mirror. But this seemingly pristine appearance hides one of the most intriguing secrets in our solar system. Beneath Europa's frozen shell lies an ocean that contains more water than all of Earth's oceans combined. The ice shell we're flying over is estimated to be 15 to 25 kilometers thick, floating on top of an ocean that may be 60 to 100 kilometers thick, 150 kilometers deep. As we glide across Europa's surface, we notice the intricate patterns of cracks and ridges that crisscross the ice like a vast puzzle. These features tell the story of a dynamic world where the ice shell is constantly being broken apart and reformed by tidal forces from Jupiter. Some of the most fascinating features we encounter are the chaos terrains, regions where the ice appears to have been completely disrupted, broken apart and refrozen in a jumbled pattern. Scientists believe these areas form when warm water from the subsurface ocean breaks through the ice shell, creating temporary lakes before freezing again. The possibility that this hidden ocean might harbor life makes Europa one of the most important targets for future exploration. Our journey continues to Ganymede, the largest moon in the entire solar system. This massive world is actually larger than the planet Mercury, and it's the only moon known to have its own magnetic field. As we approach Ganymede, we notice its surface is divided into two distinct types of terrain. Dark, heavily cratered regions represent some of the oldest surfaces in the solar system, while brighter, grooved terrains tell the story of more recent geological activity. Ganymede also hides an ocean beneath its surface, though it's buried much deeper than Europa's, beneath perhaps 150 kilometers of ice and rock layers. The existence of this buried ocean, combined with Ganymede's size and magnetic field, makes it another fascinating world in our cosmic tour. Finally, we reach Callisto, the most heavily cratered object in the solar system. This ancient moon bears the scars of 4 billion years of cosmic bombardment, its surface a museum of solar system history. Unlike the other Galilean moons, Callisto shows little sign of geological activity. Its surface is dark and heavily cratered, covered in a mixture of ice and rock that has remained largely unchanged for billions of years. But even Callisto may harbor secrets beneath its battered surface. Some evidence suggests it too might have a subsurface ocean, though much thinner and deeper than those of Europa and Ganymede. As we fly over Callisto's ancient terrain, we're looking at a world that preserves the early history of our solar system like no other place we know. The Jovian system contains dozens of other moons beyond these 4 giants, each with its own story to tell. As we prepare to leave Jupiter's gravitational domain and continue our journey outward to Saturn, we've already witnessed an incredible diversity of worlds. From the volcanic fury of Io to the hidden oceans of Europa and Ganymede, from the magnetic mysteries of Ganymede to the ancient scars of Callisto, Jupiter's moons have shown us that our solar system is far more complex and fascinating than we ever imagined. But our cosmic voyage is just beginning. Ahead of us lies Saturn, with its spectacular ring system and a collection of moons that includes some of the most bizarre and intriguing worlds in our entire solar system. Titan, with its thick atmosphere and methane lakes. Enceladus, with its icy geysers shooting into space. And dozens of other worlds, each waiting to reveal their secrets as we continue our unprecedented journey through every moon in our solar system. As we leave Jupiter's gravitational embrace behind us, our spacecraft accelerates toward the jewel of the outer solar system. Saturn appears before us like a cosmic masterpiece, its golden rings stretching across space in perfect geometric harmony. But those famous rings are just the beginning of what makes the Saturnian system one of the most captivating destinations in our solar system tour. Saturn commands a family of 83 known moons, each one a unique world shaped by different forces and histories. As we approach this ring giant, we're immediately drawn to the largest and most mysterious of Saturn's companions. Titan looms before us, shrouded in a thick orange atmosphere that completely obscures its surface from view. This is a substantial atmosphere, and it's about the only moon in our solar system with to show us landscapes unlike anything we've encountered so far. Descending through Titan's dense atmosphere feels like entering an alien world from science fiction. The atmospheric pressure here is actually 50% greater than Earth's at sea level, and it's composed primarily of nitrogen with traces of methane and other hydrocarbons. As we break through the orange haze, a landscape emerges that's both familiar and utterly alien. Rivers carved into the surface win their way toward vast lakes and seas, but these aren't filled with water. liquid methane and ethane flow through Titan's river systems and pool in lakes larger than the Great Lakes of North America. The largest of these, Kraken Mare, is bigger than the Caspian Sea and contains more hydrocarbon liquids than all of Earth's known oil and gas reserves combined. Flying low over Titan's surface, we encounter sand dunes that stretch for hundreds of kilometers, shaped by winds in this thick atmosphere. But these aren't ordinary sand dunes. They're composed of tiny particles of water ice and organic compounds, dark materials that rain down from the atmosphere like soot. The entire landscape has an otherworldly beauty, with methane clouds drifting overhead and occasional methane drizzle creating a cycle remarkably similar to Earth's water cycle, but operating at temperatures of -179 degrees Celsius. What makes Titan truly extraordinary is the complex organic chemistry happening in its atmosphere and on its surface. This moon is like a natural laboratory for prebiotic chemistry, the kind of chemical processes that might have led to life on early Earth. The thick atmosphere protects a subsurface ocean of liquid water, making Titan one of the most promising places to search for life beyond Earth. Our next destination presents a completely different spectacle. Enceladus appears as a brilliant white sphere, its surface so reflective it almost hurts to look at directly. This small moon, only about 500 kilometers across, initially seems unremarkable compared to the grandeur of Titan. But as we approach its south polar region, we witness one of the most spectacular phenomena in the entire solar system. Massive geysers of water, ice and vapor erupt from long fractures in Enceladus's surface, shooting hundreds of kilometers into space. These aren't just simple ice volcanoes. The plumes contain organic compounds, salt particles, and other materials that suggest a complex chemistry occurring beneath the moon's icy shell. We're witnessing direct evidence of a global ocean hidden beneath this moon's frozen surface. Flying through these towering plumes is like passing through a cosmic snowstorm. Ice particles glitter in the sunlight as they're launched into space at speeds of up to 400 meters per second. Some of this material escapes Enceladus entirely, helping to supply Saturn's E-ring with fresh ice particles. But most of it falls back to the surface like snow, constantly renewing the moon's bright, crater-free appearance. The fractures from which these geysers emerge have been nicknamed tiger stripes because of their distinctive appearance. These 4 parallel cracks, each about 130 kilometers long and 2 kilometers wide, are warmer than the surrounding terrain. Tidal heating from Saturn's gravity keeps these fractures active, preventing them from freezing shut and maintaining the connection between the subsurface ocean and space. What makes Enceladus particularly exciting for astrobiology is that its subsurface ocean appears to be in contact with a rocky core. This means water from the ocean can interact with rock, potentially creating the kind of chemical conditions that could support life. The geysers provide us with samples of this ocean material without the need to drill through kilometers of ice, making Enceladus one of the most accessible places to search for extraterrestrial life. As we continue our tour of Saturn's moons, we encounter worlds that challenge our understanding of what moons can be. Iapetus presents us with one of the most bizarre sights in the solar system. This moon has a 2-tone coloration so dramatic, it looks like someone painted half of it black. The leading hemisphere is as dark as charcoal, while the trailing hemisphere is as bright as fresh snow. The mystery deepens as we observe Iapetus's equatorial ridge, a mountain range that circles the moon like the seam on a walnut. This ridge reaches heights of up to 20 kilometers, making it proportionally higher than any mountain range on Earth. No one fully understands how this ridge formed, though theories range from ancient volcanic activity to the collapse of a ring system that once surrounded the Moon. Flying over Iapetus's surface reveals impact craters so large they dwarf anything we've seen before. The largest, called Turgis, is about 580 kilometers across, nearly 1/3 the diameter of the entire Moon. These massive craters tell the story of violent impacts that nearly shattered Iapetus entirely, events that occurred billions of years ago when the solar system was still a chaotic place of flying debris. Our journey takes us past dozens of smaller Saturnian moons, each with its own unique characteristics. Mimas bears a resemblance to the Death Star from science fiction, dominated by a massive crater called Herschel that gives it a distinctive appearance. Hyperion tumbles chaotically through space, its irregular shape and sponge-like surface making it one of the most unusual objects we encounter. Rhea surprises us with its own ring system, the first discovered around any moon. These tenuous rings are composed of dust and debris, probably created by micrometeorite impacts on the Moon's surface. As we fly through this ring system, we're reminded that even small moons can have complex dynamics we're only beginning to understand. The diversity of Saturn's moons reflects the complex gravitational interactions within this system. Some moons, like Prometheus and Pandora, shepherd the particles in Saturn's F-ring, keeping them confined through their gravitational influence. Others, like the co-orbital moons Janus and Epimetheus, perform an intricate dance where they actually exchange orbits every 4 years as they approach each other. As we prepare to leave the Saturnian system behind, we've witnessed worlds of ice and hydrocarbons, geysers reaching into space, and mysteries that will keep scientists busy for generations. But our cosmic tour is far from over. Beyond Saturn lies the realm of the ice giants, Uranus and Neptune, with their own collections of fascinating moons waiting to reveal their secrets. The journey outward takes us into regions of space where sunlight becomes increasingly faint and temperatures plummet to unimaginable depths. Here, in the outer reaches of our solar system, we'll encounter moons with retrograde orbits, captured comets that became permanent residents, and worlds where exotic ices create landscapes unlike anything in the inner solar system. Each destination promises new wonders and fresh mysteries as we continue our unprecedented voyage through every moon our solar system has to offer. Our spacecraft now ventures into the realm of the ice giants, where the sun appears as little more than a bright star in the eternal twilight. Uranus awaits us, that peculiar world tilted on its side like a rolling ball through space. This distant giant presents us with 27 known moons, though most are small, dark worlds that challenge our instruments to detect them against the cosmic background. As we approach the Uranian system, we immediately notice something extraordinary about this planet's orientation. Unlike every other world we've visited, Uranus spins on its side, its axis tilted 98 degrees from vertical. This means its moons orbit the planet like rings around a wheel, creating orbital dynamics unlike anywhere else in our solar system. The cause of this dramatic tilt remains one of the great mysteries we encounter on our journey. Though most scientists believe a massive collision in the distant past knocked Uranus onto its side, the largest of Uranus's moons, Titania and Oberon, appear before us as ancient, heavily cratered worlds. These moons are composed primarily of water ice mixed with rocky material, creating surfaces that tell stories of billions of years of cosmic bombardment. As we fly over Titania's terrain, we notice vast canyon systems cutting across its face, some stretching for over 1,000 kilometers. These enormous fractures suggest that Titania experienced significant geological activity in its past, possibly driven by the freezing and expansion of a subsurface ocean. Ariel presents us with one of the most geologically complex surfaces we've encountered among Uranus's moons. Bright, relatively crater-free regions contrast sharply with older, heavily cratered terrain. Deep valleys and ridges crisscross the surface, creating a landscape that speaks of relatively recent geological activity. The lack of craters in some regions suggests that this moon was resurfacing itself through internal processes as recently as a few 100 million years ago, remarkably young by solar system standards. Umbriel offers a stark contrast to its neighbor, Ariel. This dark moon reflects only 16% of the sunlight that strikes it, making it one of the darkest objects we've encountered on our journey. Its surface is heavily cratered and appears largely unchanged for billions of years. The most distinctive feature we observe is a bright ring called the Wonder Crater, a mysterious bright spot in an otherwise uniformly dark landscape that scientists still struggle to explain. Miranda provides us with perhaps the most dramatic surprise in the entire Uranian system. As we approach this small moon, only 470 kilometers across, we're stunned by the chaotic patchwork appearance of its surface. Miranda looks like it was assembled from completely different pieces, with regions of different ages and geological histories jumbled together in seemingly impossible ways. Flying over Miranda's surface reveals some of the most extreme topography we've encountered anywhere. Verona Rupes, a cliff face on this tiny world, plunges 20 kilometers straight down, making it the tallest cliff known in our solar system. If you could somehow stand at the edge of this precipice and jump, you would fall for about 10 minutes in Miranda's weak gravity before finally hitting the bottom. The origin of Miranda's bizarre appearance has puzzled scientists since the Voyager spacecraft first revealed it in detail. One theory suggests that this moon was completely shattered by a massive impact in the distant past, then reassembled itself through gravitational attraction. The different regions we observe might represent pieces of the original moon's core and mantle that were mixed together during this catastrophic event and subsequent reassembly. As we leave the Uranian system behind, our journey takes us even further from the sun's warmth to Neptune, the windiest world in our solar system. Neptune's deep blue color grows larger in our view as we approach, and we begin to make out its largest moon, Triton, a world that immediately captures our attention with its unique characteristics. Triton stands apart from every other large moon we've encountered because of one remarkable fact. It orbits Neptune backward in what astronomers call a retrograde direction. This tells us that Triton wasn't born in the Neptunian system like most moons. Instead, it's almost certainly a captured Kuiper Belt object, a dwarf planet that wandered too close to Neptune and was gravitationally captured billions of years ago. This capture event was catastrophic for Neptune's original moon system. Computer simulations suggest that when Triton arrived, its powerful gravity disrupted and destroyed most of Neptune's existing moons, leaving behind only a few small, irregularly shaped survivors that we encounter as we explore the system. As we descend toward Triton's surface, we discover a world unlike any we've visited. Despite being farther from the sun than any large moon we've explored, Triton shows signs of remarkable geological activity. Dark streaks across its southern hemisphere mark the locations of active geysers, nitrogen plumes that shoot 8 kilometers into the thin atmosphere before being blown hundreds of kilometers across the surface by high-altitude winds. These nitrogen geysers operate through a process we haven't seen anywhere else. Dark material beneath Triton's surface absorbs the faint sunlight, creating enough heat to vaporize subsurface nitrogen ice. The pressure builds until it erupts through weak spots in the surface, creating spectacular plumes that paint dark streaks across the bright nitrogen ice plains. Flying across Triton's surface reveals a world of incredible diversity packed into a sphere only slightly larger than Earth's moon. We pass over vast plains of nitrogen ice, their surfaces smooth and relatively crater-free, suggesting they're geologically young. Cantaloupe terrain, so named because it resembles the skin of that fruit, covers large regions with mysterious ridges and valleys that may have formed through some form of convective process in the moon's interior. The temperature on Triton's surface hovers around -235 degrees Celsius, making it one of the coldest places we've encountered. Yet this extreme cold preserves a thin atmosphere composed primarily of nitrogen, creating seasonal changes as different parts of the moon face toward or away from the distant sun during Neptune's 165-year orbit. What makes Triton particularly fascinating is that it's slowly spiraling inward toward Neptune. The tidal forces that keep it geologically active are also stealing energy from its orbit, causing it to gradually fall toward its parent planet. In perhaps 3.5 billion years, Triton will either crash into Neptune or be torn apart by tidal forces, creating a spectacular ring system that will rival Saturn's in grandeur. Neptune's other moons present us with a collection of small, irregular worlds that are probably captured asteroids or comets. Nereid follows one of the most eccentric orbits of any moon in the solar system, swinging from 1.5 million kilometers away from Neptune to over 9 million kilometers in its highly elongated path. This extreme orbit takes it almost a full Earth year to complete, and the varying distance causes dramatic changes in the amount of sunlight it receives. As we explore the outer reaches of the Neptunian system, we encounter moons with names like Proteus, Larissa, and Galatea. These small dark worlds bear the scars of countless impacts and show little sign of geological activity. They're remnants of the chaos that ensued when Triton arrived in the system, survivors of a gravitational catastrophe that reshaped the entire Neptunian family of moons. Our journey through the ice giant's domain reveals how different the outer solar system is from the inner worlds we explored earlier. Here, in the realm of perpetual twilight, moons are composed primarily of various ices mixed with rocky material. Water ice, as hard as granite in these temperatures, forms the bedrock of most surfaces. Nitrogen, methane, and carbon monoxide ices create exotic landscapes that would be impossible closer to the sun's warmth. The moons of Uranus and Neptune also show us how orbital dynamics can create unique evolutionary paths. The extreme tilt of Uranus subjects its moons to seasonal changes that last for decades, with each hemisphere experiencing 42 years of continuous daylight followed by 42 years of darkness. These extreme seasons may drive atmospheric and surface changes that we're only beginning to understand. As we prepare to leave Neptune behind and venture into the farthest reaches of our solar system, we've witnessed worlds where nitrogen geysers pierce the darkness, where ancient impacts created some of the most extreme topography known, and where captured dwarf planets become moons in gravitational dances that will ultimately prove fatal. The ice giants have shown us that even in the cold, distant reaches of our solar system, dynamic processes continue to shape and reshape these ancient worlds. But our cosmic voyage isn't finished yet. Beyond Neptune lies the realm of the dwarf planets, worlds like Pluto that command their own systems of moons. Here, at the very edge of our solar system's gravitational influence, we'll encounter the most distant moons of all, worlds where the sun provides less light than a full moon does on Earth, and where the mysteries of our solar system's formation and evolution await our discovery. Our spacecraft now embarks on the final leg of our cosmic odyssey, venturing beyond the realm of the major planets into the mysterious Kuiper Belt, where dwarf planets reign as kings of their own miniature kingdoms. Here, in the twilight zone of our solar system, distances become almost incomprehensible, and sunlight fades to little more than starlight. Pluto emerges from the cosmic darkness like a russet jewel, accompanied by its largest companion, Charon. What we're witnessing here is something extraordinary. A double planet system where two worlds orbit so close to each other they're tidally locked in an eternal dance. Pluto and Charon always show the same face to each other, like cosmic partners frozen in an endless waltz. As we approach this binary system, the first thing that strikes us is the scale. Charon is more than half the size of Pluto itself, making this the most evenly matched planet-moon pairing we've encountered anywhere in our solar system. From Pluto's surface, Charon would appear 7 times larger in the sky than our moon appears from Earth, a massive grey sphere hanging motionless in the heavens. Descending toward Pluto's surface, we discover a world far more complex and beautiful than anyone imagined before the New Horizons spacecraft revealed its secrets. The heart-shaped Tombor Regio dominates one hemisphere, a vast plain of nitrogen ice so smooth and young that it bears almost no impact craters. This frozen sea tells the story of geological processes still active on a world 4 billion miles from the Sun. Flying across Pluto's diverse terrain feels like exploring multiple worlds compressed into one small sphere. We pass over towering mountains of water ice that rise 4 kilometers above the surrounding plains, their peaks sharp and jagged like the Alps on Earth. These mountains float like icebergs in a sea of nitrogen ice, their water ice composition as hard as granite in the extreme cold of the outer solar system. The most stunning features we encounter are the cellular planes within Tombor Regio, polygonal patterns in the nitrogen ice that stretch for kilometers across. These mysterious formations appear to be convection cells, created by slow circulation of nitrogen ice over geological timescales. Warmer nitrogen ice rises from below, spreads across the surface, then cools and sinks back down, creating patterns that shift and evolve over thousands of years. Dark streaks and dunes composed of methane particles paint abstract patterns across Pluto's surface, shaped by winds in the dwarf planet's thin atmosphere. This atmosphere, though incredibly tenuous, creates weather systems and seasonal changes as Pluto's elliptical orbit carries it closer to and farther from the Sun over its 248-year journey around our star. Charon presents a completely different landscape as we fly across its ancient, heavily cratered surface. This moon bears the scars of billions of years of impacts, its northern hemisphere dominated by plains that may once have been covered by a subsurface ocean that later froze and expanded, cracking the surface like a broken eggshell. The southern hemisphere reveals some of the most dramatic topography we've encountered, with canyons that make Earth's Grand Canyon look modest by comparison. The most striking feature on Charon is its dark polar cap, composed of materials that may have been transferred from Pluto's atmosphere over millions of years. This reddish-brown material, likely organic compounds called tholins, creates a mysterious dark region that contrasts sharply with the brighter grey of Charon's water ice surface. What makes the Pluto-Charon system truly remarkable is their gravitational relationship. Unlike any other planet-moon pair we've visited, these two worlds orbit around a point in space between them, technically making them a binary system rather than a planet with a satellite. This unique arrangement has shaped both worlds throughout their history, with tidal forces keeping them locked in their eternal dance while gradually synchronizing their rotation periods. But Pluto's family doesn't end with Charon. 4 smaller moons orbit this distant system, each one a tiny world with its own story to tell. Nix and Hydra, the largest of these smaller companions, are elongated objects that tumble chaotically through space. Unlike most moons we've encountered, these don't keep the same face pointed toward their parent body. Instead, They spin unpredictably, their rotation periods changing due to the complex gravitational influences of both Pluto and Charon. Styx and Kerberos, the smallest members of Pluto's family, are so tiny they're barely more than cosmic pebbles, only a few kilometers across. These miniature moons may be fragments left over from the ancient collision that created the Pluto-Charon system, or they might be captured Kuiper Belt objects that wandered too close and became permanent residents of this distant realm. The formation of Pluto's entire moon system likely traces back to a catastrophic impact billions of years ago, similar to the giant impact that created Earth's moon. A large Kuiper Belt object probably collided with early Pluto, blasting material into orbit that eventually coalesced into Charon and the smaller moons. This violent origin story explains why Charon is so large relative to Pluto and why the entire system shares such unusual orbital characteristics. As we venture deeper even into the Kuiper Belt, we encounter other dwarf planets commanding their own retinues of moons. Eris, slightly smaller than Pluto but more massive, hosts a single known companion called Dysnomia. This moon orbits its parent at a distance similar to that between Earth and our moon, but in the frigid depths of the outer solar system, where temperatures hover around -240 degrees Celsius. Haumea presents us with one of the strangest systems we've encountered on our entire journey. This elongated dwarf planet spins so rapidly that it's stretched into an ellipsoid shape, rotating once every 4 hours. Its two known moons, Hi'iaka and Namaka, orbit this tumbling football-shaped world in a system that challenges our understanding of orbital mechanics. The rapid rotation of Haumea may have been caused by the same impact that created its moons, flinging material into space that eventually formed these distant companions. Makemake, another denizen of the Kuiper Belt, remained moonless for years after its discovery, until astronomers finally detected its small, dark companion, provisionally designated S/2015-136472-1. This tiny moon is so faint and close to its bright parent that it required the most advanced telescopic techniques to detect, reminding us how much we still have to learn about these distant systems. The moons of the dwarf planets represent some of the most pristine objects in our solar system, largely unchanged since their formation over 4 billion years ago. These ancient worlds preserve clues about the conditions that existed during the solar system's youth, when planets were still assembling from the debris of stellar formation. Each moon we've encountered in the Kuiper Belt tells part of the story of how our solar system evolved from a disk of dust and gas around the young sun into the complex collection of worlds we see today. The impacts that created these moon systems also shaped the surfaces of planets throughout the solar system, including Earth. The Late Heavy Bombardment, a period of intense cosmic impacts about 4 billion years ago, may have been triggered by gravitational interactions among the giant planets that sent Kuiper Belt objects careening throughout the inner solar system. What strikes us most profoundly as we fly through these distant systems is the incredible diversity of worlds our solar system contains. From the volcanic fury of Io to the methane lakes of Titan, from the geysers of Enceladus to the ancient scars of Callisto, from the nitrogen plains of Pluto to the chaotic tumbling of Miranda, each moon in planetary formation and evolution represents a unique experiment. Some of these worlds harbor subsurface oceans that may contain more water than all of Earth's seas combined. Others preserve organic compounds that could hold clues to the origin of life itself. Many bear the signatures of geological processes we never imagined could operate so far from the sun's warmth, driven by tidal heating, radioactive decay, or chemical reactions we're only beginning to understand. The moons we visited also reveal the incredible violence that characterized our solar system's early history. Every heavily cratered surface tells the story of the late heavy bombardment, when asteroids and comets rained down on every solid surface in reach. The smooth, crater-free regions on moons like Europa and Enceladus show us that geological activity continues to reshape these worlds, erasing the scars of ancient impacts and creating new landscapes through internal processes. Our journey has also shown us how gravitational interactions can create some of the most beautiful and complex dynamics in nature. The orbital resonances that control the motions of Jupiter's moons, the tidal heating that powers Io's volcanoes, the shepherding effects that maintain Saturn's rings, and the chaotic rotations of small, irregular moons, all demonstrate the elegant mathematics underlying celestial mechanics. As we prepare to conclude our unprecedented tour of every moon in our solar system, we find ourselves profoundly changed by what we've witnessed. We've seen worlds where diamond rain falls through alien skies, where ancient impacts created mountains taller than Everest, where subsurface oceans may harbor life forms unlike anything on Earth, and where the very definition of what constitutes a moon stretches to encompass objects as diverse as captured asteroids and co-orbital companions. The 200+ moons we've encountered represent an astounding variety of sizes, compositions, and evolutionary histories. Some are larger than planets, others smaller than cities. Some harbor thick atmospheres, others exist in perfect vacuum. Some are geologically active, constantly reshaping their surfaces, while others preserve pristine records of events that occurred billions of years ago. Perhaps most remarkably, our journey has revealed that moons aren't simply passive companions to their parent planets. They're dynamic worlds with their own weather systems, geological processes, and potentially even their own forms of life. The traditional view of moons as dead, crater-covered rocks has been completely revolutionized by the discoveries we've witnessed on our cosmic voyage. The subsurface oceans of Europa, Enceladus, and Ganymede may represent the most likely places in our solar system to find extraterrestrial life. These hidden seas, warmed by tidal heating and possibly in contact with rocky cores, could provide the energy and chemical complexity necessary for biology to emerge and evolve. The organic chemistry laboratories of Titan, where complex hydrocarbons rain from thick orange skies, offer another tantalizing glimpse into the chemical processes that might have preceded life on early Earth. This distant moon operates like a vast natural experiment in prebiotic chemistry, synthesizing organic molecules through atmospheric processes that mirror conditions our own planet may have experienced billions of years ago. Our cosmic odyssey has also revealed the incredible resilience of geological processes operating under the most extreme conditions imaginable. On Triton, nitrogen geysers function at temperatures that would instantly freeze any water solid, yet this moon maintains an active geology powered by the faint warmth of our distant sun. The fact that worlds so far from any significant heat source can remain geologically active challenges our understanding of planetary evolution and suggests that habitable conditions might exist in places we never thought possible. The shepherd moons of Saturn demonstrate how even the smallest objects can exert profound influences on their environments. These tiny worlds, some no larger than mountains, maintain the intricate structure of Saturn's rings through their gravitational shepherding, proving that size doesn't always determine significance in the cosmic dance of celestial mechanics. As we reflect on the shepherd moons and ring systems we've encountered, we're reminded that our journey has revealed multiple types of ring systems throughout the outer solar system. Not just Saturn's magnificent displays, but also the tenuous rings of Jupiter, Uranus, and Neptune, each maintained and shaped by the gravitational influence of nearby moons. Even individual moons like Rhea have been found to possess their own ring systems, suggesting that these structures might be more common than we ever imagined. The retrograde moons we've encountered, like Triton and many of the irregular satellites of the gas giants, tell stories of cosmic catastrophes and gravitational captures that reshaped entire planetary systems. These backwards orbiting worlds are time capsules from the era when our solar system was still settling into its current configuration, when massive migrations of the giant planets sent countless objects careening through space to find new homes around distant suns. The co-orbital moons of Saturn, Janus, and Epimetheus have shown us orbital mechanics so exotic they seem almost impossible. These two moons literally trade orbits every few years, approaching each other, exchanging gravitational energy, and swapping positions in a cosmic ballet that continues to astound astronomers. Their existence proves that stable orbital configurations can take forms far more complex than the simple ellipses most people imagine. Throughout our journey, we've witnessed the profound influence that Jupiter has exerted on the entire solar system through its massive gravitational field. This giant planet has acted as both protector and destroyer, capturing comets and asteroids that might otherwise have impacted the inner planets, while simultaneously flinging other objects into chaotic orbits that sent them careening throughout the solar system. The scars on every moon we've visited bear testimony to Jupiter's dual role in shaping our cosmic neighborhood. The tidal heating we've observed operating on so many moons reveals energy sources that dwarf anything available on Earth. The constant flexing and stretching caused by gravitational interactions generates enough heat to melt rock, drive volcanic eruptions, and maintain subsurface oceans for billions of years. This mechanism provides a way for worlds to remain active and potentially habitable, even in the frozen outer reaches of our solar system, where solar energy is virtually non-existent. Our expedition has also demonstrated the incredible precision required for stable orbital systems to exist at all. The resonances that lock moons into predictable patterns, the balance between gravitational attraction and centrifugal force that prevents them from either crashing into their parent planets or flying off into space, and the delicate equilibrium that maintains ring systems all depend on mathematical relationships so exact they seem almost designed. The irregular shapes of many smaller moons tell stories of cosmic violence and gravitational capture. These potato-shaped worlds, like Phobos and Deimos around Mars, or the many irregular satellites of the gas giants, are probably captured asteroids that wandered too close to massive planets and found themselves permanently trapped in elliptical, often highly inclined orbits. Their dark surfaces and unusual compositions mark them as foreigners in their adopted planetary systems. The seasonal changes we've observed on moons like Titan and Triton remind us that these worlds experience weather and climate variations just like planets do. Titan's methane cycle creates seasons of hydrocarbon precipitation and evaporation, while Triton's nitrogen atmosphere undergoes dramatic changes as different regions face toward or away from the distant Sun during Neptune's incredibly long orbital period. The magnetic fields we've encountered, particularly around Ganymede, reveal complex interior structures and dynamic processes operating deep within these worlds. Ganymede's magnetic field, the only one known around any moon, suggests a differentiated interior with a liquid iron core, making this moon more like a small planet than a simple satellite. This discovery has revolutionized our understanding of how large moons can evolve and maintain geological activity over billions of years. The ancient surfaces of moons like Callisto preserve records of the solar system's violent youth better than any other objects we know. These heavily cratered worlds serve as cosmic museums, their surfaces recording every major impact event from the past 4 billion years. By studying the crater populations on different moons, scientists can piece together the chronology of solar system bombardment and understand how the rate of cosmic impacts has changed over time. The subsurface oceans we've discovered beneath the icy shells of multiple moons represent some of the largest bodies of liquid water in the entire solar system. Europa's ocean may contain twice as much water as all of Earth's oceans combined, while the hidden seas beneath Enceladus, Ganymede, and other worlds add up to water reserves that dwarf our home planet's hydrosphere. These discoveries have fundamentally altered our perspective on where liquid water and potentially life might exist in the cosmos. The cryovolcanism we've witnessed on moons like Enceladus and Triton demonstrates that volcanic activity can occur even at temperatures hundreds of degrees below freezing. These ice volcanoes erupt water, ammonia, and other volatile compounds instead of molten rock, creating geological processes unlike anything on Earth, yet following the same basic principles of pressure buildup and explosive release. The captured nature of many outer planet moons tells the story of our solar system's dynamic evolution. These former asteroids and Kuiper Belt objects that became moons through gravitational capture represent immigrants from distant regions of space, bringing with them compositions and characteristics that reflect conditions far from their current homes. Their presence around the giant planets demonstrates the powerful reach of these massive worlds' gravitational influence. The complex orbital relationships we've observed, from simple tidal locking to exotic resonances to chaotic rotation states, reveal the full spectrum of gravitational interactions possible between celestial bodies. Some moons maintain perfectly synchronous rotations, always showing the same face to their parent planets, while others tumble unpredictably through space, their rotation periods changing due to the complex interplay of multiple gravitational influences. As our unprecedented journey draws toward its conclusion, we find ourselves contemplating not just the individual wonders of each moon we visited, but the incredible interconnectedness of the entire solar system. Every moon, from the largest to the smallest, plays a role in the cosmic symphony of gravitational interactions that has shaped our local neighborhood for over 4 billion years. The diversity of processes we've witnessed operating throughout our solar system's family of moons suggests that similar diversity likely exists around other stars throughout our galaxy. If our single star system can produce such an astounding variety of worlds, each with its own unique characteristics and evolutionary history, then the cosmos must contain countless variations on these themes. Worlds beyond our current imagination, harboring processes and phenomena we've never conceived. The search for life beyond Earth has been transformed by our journey through these diverse worlds. No longer do we look only for planets in the habitable zones around their stars. Now we understand that moons throughout a planetary system might harbor conditions suitable for life, heated by tidal forces, protected by magnetic fields, and supplied with the chemical ingredients necessary for biology through interactions with rocky cores and cosmic bombardment. The technological challenges of exploring these distant worlds continue to inspire innovations in spacecraft design and mission planning. Each successful flyby, orbital insertion, and surface landing teaches us new lessons about operating in the extreme environments of the outer solar system, where solar panels become ineffective and radio signals take hours to travel between Earth and distant spacecraft. Our cosmic voyage has revealed that the concept of a moon encompasses an incredible range of objects, from captured asteroids to differentiated worlds larger than planets, from ancient cratered relics to geologically active spheres constantly reshaping their surfaces. This diversity challenges our traditional categorizations and forces us to think more broadly about what kinds of objects can exist in planetary systems. The role of impacts in shaping moon surfaces and creating moon systems themselves has emerged as a central theme throughout our journey. From the giant impact that likely created Earth's moon, to the collision that formed the Pluto-Charon system, from the bombardment that scarred Callisto, to the impacts that may have shattered and reassembled Miranda. Cosmic collisions have been the primary sculptors of the worlds we've explored. The seasonal cycles operating on moons with substantial atmospheres like Titan demonstrate that complex climate systems can develop even on bodies much smaller than planets. These atmospheric dynamics create weather patterns, seasonal changes, and long-term climate evolution that rival anything we see on planetary bodies, proving that interesting meteorology isn't limited to large worlds with thick atmospheres. The preservation of organic compounds in the cold outer reaches of the solar system has important implications for understanding how the building blocks of life might be distributed throughout the cosmos. The complex chemistry we've observed on moons like Titan and in the plumes of Enceladus suggests that the molecular ingredients for biology might be common throughout planetary systems, waiting for the right conditions to begin the long journey toward living organisms. The gravitational resonances we've encountered throughout our journey reveal the hidden mathematical order underlying what might appear to be cosmic chaos. These precise relationships between orbital periods create stability in systems that should theoretically be unstable, like celestial clockwork ticking away for billions of years. The Galilean moons of Jupiter demonstrate this perfectly, with Io, Europa, and Ganymede locked in a 4:2:1 resonance that has persisted since the solar system's youth. But resonances can also be destructive forces. The gaps in Saturn's rings, swept clean by gravitational resonances with various moons, show us how these same mathematical relationships can prevent objects from maintaining stable orbits. What creates harmony in one location becomes a zone of instability in another, demonstrating the delicate balance that governs all celestial mechanics. As we venture toward the very edge of our solar system's gravitational influence, we encounter the most distant moons of all. These objects exist in a realm where the sun's gravitational pull becomes so weak that the slightest perturbation from passing stars or interstellar winds could send them tumbling into the void. Yet somehow they persist, clinging to their parent bodies through gravitational bonds so tenuous they seem almost miraculous. The extreme distances we're now traversing challenge our understanding of what constitutes a bound system. Some of the outermost irregular satellites of the giant planets orbit so far from their parents that their orbital periods stretch for years. These distant wanderers spend most of their time in regions where the sun's gravitational influence nearly equals that of their host planets, creating orbital dynamics so complex they require supercomputers to model accurately. The temperatures we encounter in these outer reaches drop to levels that transform familiar substances into exotic materials. Nitrogen becomes as solid as granite. Methane freezes into ice harder than steel. Even hydrogen begins to behave in ways that would seem impossible in the warmer regions closer to the sun. These extreme conditions create landscapes of crystalline beauty, where frozen gases form towering cliffs and deep valleys carved by processes we're only beginning to understand. The lighting conditions in the outer solar system create an ethereal beauty unlike anything in the inner system. Here, where the sun appears as little more than a bright star, the primary illumination often comes from reflected light, bouncing between moons, or from the faint glow of planetary magnetospheres interacting with charged particles from space. This ghostly illumination reveals surfaces and atmospheric phenomena invisible to eyes adapted to Earth's bright daylight. The organic chemistry we've discovered operating in these frigid environments suggests that complex molecular processes can occur under conditions far more extreme than we once thought possible. The dark reddish compounds coating many outer system moons result from radiation processing of simple hydrocarbons over millions of years, creating materials that might hold clues to the chemical evolution that preceded life on Earth. The magnetic environments surrounding the giant planets create some of the most dynamic and violent conditions in the solar system. Charged particles accelerated to incredible energies by planetary magnetic fields bombard moon surfaces, creating aurora displays and driving chemical reactions that would be impossible in calmer environments. These radiation environments are so intense, they would quickly prove fatal to any unprotected human visitor, yet they also drive fascinating processes that continuously alter moon surfaces and thin atmospheres. The dust dynamics we observe in the outer solar system reveal how even the smallest particles play crucial roles in shaping larger structures. Microscopic grains blasted from moon surfaces by micrometeorite impacts feed ring systems, create tenuous atmospheres, and even influence the orbits of larger objects through subtle radiation pressure effects. This interconnectedness shows us that no component of a planetary system exists in isolation. The escape of atmospheric gases from moons throughout the outer solar system creates invisible connections between these worlds and the interplanetary medium. Atoms from Io's volcanic eruptions eventually reach Jupiter's magnetosphere. Water molecules from Enceladus's geysers supply Saturn's E-ring with fresh material. Even the thin atmospheres of distant moons like Triton slowly leak into space, carrying with them the chemical signatures of processes occurring on their surfaces. The ancient surfaces of many outer system moons preserve impact crater populations that tell stories stretching back to the solar system's formation. These cratered terrains serve as natural laboratories for understanding how bombardment rates have changed over billions of years. By comparing crater densities between different regions and different moons, scientists can piece together a chronology of cosmic violence that shaped every solid surface in our solar system. The subsurface structures we've inferred beneath many icy moons suggest layered compositions of incredible complexity. Water oceans sandwiched between layers of different ice phases, rocky cores surrounded by mantles of exotic high-pressure ices, and possibly even multiple ocean layers separated by solid barriers, create internal architectures unlike anything we see on terrestrial worlds. The tidal forces operating throughout moon systems create energy sources that can persist for billions of years. Unlike the nuclear fusion that powers stars or the radioactive decay that heats planetary interiors, tidal heating depends only on orbital mechanics and can continue as long as gravitational interactions maintain orbital eccentricity. This makes tidal heating potentially the most long-lived energy source available to any world in the cosmos. The photochemistry occurring in the thin atmospheres of distant moons demonstrates how even minute amounts of atmospheric gases can support complex chemical processes. Ultraviolet light from the distant sun, cosmic radiation, and charged particles from planetary magnetospheres all contribute to breaking apart simple molecules and reassembling them into more complex compounds. These processes create the organic hazes and surface deposits that give many outer system moons their distinctive colors and compositions. The seasonal variations we observe on moons with eccentric orbits or tilted parent planets create climate cycles that can span human lifetimes or even centuries. Imagine seasons where winter lasts for decades, or where the intensity of sunlight varies by factors of 2 or more over the course of a single orbit. These extreme seasonal variations drive atmospheric dynamics and surface processes unlike anything we experience on Earth. The crystalline structures of water ice under the extreme conditions found in the outer solar system take forms that don't exist naturally on Earth. High-pressure ice phases, with densities approaching that of liquid water, create materials with properties we're only beginning to understand. These exotic ice forms may play crucial roles in the internal dynamics of large icy moons, affecting everything from ocean circulation to the transfer of heat from radioactive cores. The capture mechanisms that brought irregular satellites into orbit around the giant planets represent some of the most dramatic gravitational encounters in solar system history. These events, which may have occurred when the planets were still migrating through the outer solar system, involve three-body interactions of incredible complexity. Objects that should have simply flown past massive planets instead found themselves captured into highly elliptical, often retrograde orbits that persist to this day. The binary nature of many small outer system objects reveals that multiple body systems are common even among the smallest members of planetary families. These paired objects, sometimes separated by only a few kilometers, orbit around their common center of mass while simultaneously orbiting their parent planet. The gravitational dynamics of such systems push orbital mechanics to its limits, creating configurations that seem almost impossible, yet clearly exist throughout the outer solar system. The color variations we observe across moon surfaces often reflect different compositions or different degrees of space, weathering, and radiation processing. The bright whites of fresh ice contrast with the dark greys and browns of organic compounds, while reddish hues often indicate the presence of sulfur compounds or radiation-processed organics. These color patterns create maps of geological and chemical processes operating over vast timescales. The ring-moon interactions we've witnessed around Saturn demonstrate how solid objects can maintain complex gravitational relationships with particulate systems. Shepherd moons confine ring particles to narrow bands, while embedded moonlets create gaps and waves that propagate through ring systems like ripples in a cosmic pond. These interactions reveal the fluid-like behavior of ring systems despite being composed of countless individual particles. The atmospheric escape processes operating on moons throughout the solar system show us how worlds can lose their gaseous envelopes over geological time. From the rapid loss of hydrogen from warm inner system objects to the slow sublimation of nitrogen from the surfaces of distant ice worlds, these processes demonstrate that atmospheres are dynamic, evolving systems that can appear, thicken, thin, and completely disappear over cosmic time. The impact gardening that continuously stirs the upper layers of moon surfaces creates complex mixtures of materials from different sources. Local bedrock mingles with debris from distant impacts, creating regoliths that preserve samples from across entire planetary systems. This process makes every moon surface a natural museum of materials from throughout its cosmic neighborhood, waiting to be decoded by future explorers. The magnetic field interactions between moons and their parent planets create some of the most spectacular auroral displays in the solar system. When moons with conducting layers or thin atmospheres pass through planetary magnetic fields, they generate electrical currents that paint glowing footprints in their parent planet's upper atmospheres. These auroral footprints serve as remote probes of moon properties, allowing us to study internal structures without landing spacecraft on their surfaces. The thermal evolution of moons over billions of years creates the diverse landscapes we observe today. Initially hot from accretion and radioactive decay, these worlds have cooled at different rates depending on their size, composition, and orbital environment. Some retain enough internal heat to drive active geology, while others have frozen into the configurations they achieved early in their histories. The chemical differentiation that occurred in larger moons during their formation separated heavy elements from lighter ones, creating layered internal structures similar to terrestrial planets. These differentiated interiors generate their own magnetic fields, drive convective processes, and maintain the geological activity that keeps some moon surfaces young and dynamic. Our journey through every moon in the solar system has revealed a cosmos far more diverse and active than anyone imagined when humans first pointed telescopes at the night sky. We've witnessed worlds where the familiar becomes alien and the impossible becomes routine, where ice flows like lava, and where ancient impacts created features that dwarf any earthly mountain range. The sheer number of moons we've encountered, more than 200 confirmed worlds with new ones being discovered regularly, suggests that moon systems are fundamental features of planetary formation. Almost every planet beyond Mars hosts multiple moons, and even some asteroids have been found to possess their own tiny companions. This ubiquity implies that gravitational capture and collision-induced formation of satellite systems are natural consequences of planetary evolution. The range of sizes we've explored, from moonlets smaller than city blocks to satellites larger than Mercury, demonstrates that there's no typical size for a moon. Each represents a different outcome of the complex gravitational and collisional processes that shaped our solar system during its chaotic youth. The largest moons are worlds in their own right, with internal structures and geological processes that rival those of planets. The variety of compositions we've encountered reflects the different regions of the solar system where these objects formed and the different processes that brought them to their current locations. Rocky moons near the inner edge of planetary systems, icy worlds in the outer regions, and mixed compositions that tell stories of migration and gravitational stirring throughout solar system history. The geological processes we've observed operating under conditions of extreme cold, low gravity, and exotic atmospheric compositions expand our understanding of how worlds can evolve and remain active. Tidal heating, radioactive decay, and chemical reactions driven by radiation processing provide energy sources that can maintain geological activity for billions of years, even in environments that seem utterly hostile to any form of change. The discovery of subsurface oceans beneath the ice shells of multiple moons has revolutionized our understanding of where liquid water and potentially life might exist in the cosmos. These hidden seas, warmed by tidal heating and protected from the harsh radiation environment of space, may provide stable habitats that could persist far longer than the temporary surface oceans of planets in stellar habitable zones. As our cosmic odyssey finally draws to its close, we find ourselves transformed by the incredible diversity and beauty we've witnessed. Every moon we've visited has contributed to a growing appreciation for the complexity and interconnectedness of planetary systems, revealing processes and phenomena that continue to challenge our understanding of how worlds form, evolve, and potentially harbor life. The technological achievements that have made this journey possible, from robotic spacecraft that have visited dozens of these worlds to telescopes that can detect moons orbiting distant planets, represent some of humanity's greatest accomplishments. Each successful mission to explore these alien landscapes has expanded our cosmic perspective and brought us closer to answering fundamental questions about our place in the universe. The future exploration of these worlds promises discoveries that will continue to reshape our understanding of planetary science, astrobiology, and the potential for life beyond Earth. Missions currently being planned will drill through ice shells to sample subsurface oceans, land on the surfaces of moons where no spacecraft has ever touched down, and search for signs of past or present biological activity in environments we now know could support life. Our flight through every moon in the solar system has shown us that we live in a universe of incredible richness and diversity. where worlds beyond number wait to reveal their secrets to curious explorers. From the volcanic oceans of Europa, from the meth fury of Io, to the Hiddenane lakes of Titan, to the ancient scars of Callisto, each moon represents a unique experiment in planetary evolution, a laboratory where the laws of physics and chemistry have created wonders beyond imagination. As we prepare to return from this unprecedented journey through our solar system's family of moons, we carry with us a profound appreciation for the cosmic processes that have shaped these worlds and continue to drive their evolution. We've seen how gravity sculpts landscapes, how impacts create and destroy, how chemistry operates under extreme conditions, and how life might find ways to emerge and thrive in environments we once thought utterly barren. The story of these moons is still being written, with new chapters added by every space mission, every telescopic observation, and every theoretical insight that helps us better understand these distant worlds. Our journey has shown us that exploration is not just about visiting new places, but about discovering new ways of understanding the universe and our place within it. The moons of our solar system have taught us that wonder and beauty exist wherever we have the curiosity and courage to look for them. The future missions being planned to these extraordinary worlds will push the boundaries of human engineering and scientific capability. Spacecraft designed to survive the intense radiation around Jupiter, drill through kilometers of ice to reach hidden oceans, and navigate the complex gravitational fields of multiple moon systems, simultaneously represent technological challenges that inspire innovations benefiting life here on Earth. The gravitational resonances we've discovered throughout our journey reveal mathematical relationships so precise they seem almost orchestrated by some cosmic conductor. These orbital harmonies, where moons complete their orbits in exact ratios to one another, create stability in systems that should theoretically tear themselves apart. The precision required for these relationships to persist over billions of years demonstrates the elegant underlying order that governs celestial mechanics. What strikes us most profoundly as we reflect on our cosmic voyage is how each moon we've encountered tells part of a larger story about planetary formation and evolution. The heavily cratered surfaces preserve records of the late heavy bombardment. The smooth plains reveal ongoing geological processes. The captured irregular satellites document the chaotic migrations of the giant planets early in solar system history. The search for biosignatures on these worlds has evolved far beyond simply looking for liquid water. We now understand that life, if it exists on these moons, might take forms so alien that we're only beginning to develop the tools and techniques necessary to detect it. The organic chemistry laboratories of the outer solar system may be conducting experiments in biology using completely different chemical pathways than anything we see on Earth. The magnetic field measurements we've made around various moons provide windows into their internal structures that would be impossible to obtain any other way. When Ganymede's magnetic field was discovered, it revealed not just a differentiated interior, but active processes occurring deep within this ancient world. These magnetic signatures serve as cosmic X-rays, allowing us to peer inside moons without ever landing on their surfaces. The seasonal changes we've observed on moons with substantial atmospheres demonstrate that complex meteorological systems can develop on bodies much smaller than planets. Titan's methane cycle creates weather patterns that rival Earth's water cycle in complexity, while the seasonal sublimation and condensation of nitrogen on Triton drives atmospheric dynamics that change dramatically over Neptune's long orbital period. The cryovolcanic activity we've witnessed represents one of the most spectacular phenomena in the outer solar system. These eruptions of water, ammonia, and other volatile compounds create geological features unlike anything on Earth, yet they follow the same basic principles of pressure buildup and explosive release that drive terrestrial volcanism. The geysers of Enceladus, shooting material hundreds of kilometers into space, provide direct samples of a subsurface ocean without requiring us to drill through the ice shell. The role of radiation in shaping moon surfaces and driving chemical reactions has emerged as a crucial factor in outer solar system evolution. High-energy particles trapped in planetary magnetospheres continuously bombard moon surfaces, breaking apart simple molecules and reassembling them into complex organic compounds. This radiation chemistry creates the dark, reddish materials that coat many outer system moons and may represent a significant source of organic molecules throughout the cosmos. The tidal heating mechanisms we've observed operating throughout moon systems provide energy sources that can persist far longer than stellar heating or radioactive decay. As long as orbital eccentricity is maintained through gravitational interactions, tidal forces will continue to flex and heat moon interiors, potentially maintaining habitable conditions for billions of years, even around dead stars. The impact processes that created many of these moon systems also distributed materials throughout planetary neighborhoods in ways that continue to influence evolution today. The collision that formed Earth's moon scattered debris throughout the inner solar system. The impacts that created the irregular satellite populations around the gas giants brought materials from the asteroid belt and Kuiper belt into the outer system, creating chemical mixing on a scale that spans the entire solar system. The atmospheric escape processes we've documented show how moons can lose their gaseous envelopes through various mechanisms. From thermal escape driven by solar heating to sputtering caused by energetic particle bombardment, these processes demonstrate that atmospheres are dynamic systems that can appear, evolve, and disappear over geological timescales. The binary and multiple moon systems we've encountered reveal gravitational dynamics so complex they challenge our computational models. Objects orbiting common centers of mass while simultaneously orbiting parent planets create three-body problems that require sophisticated mathematical techniques to solve. These systems exist in delicate gravitational balance, yet they persist for billions of years without flying apart or colliding. The ring-moon interactions we've observed around the gas giants demonstrate how solid objects can control the behavior of countless individual particles through gravitational shepherding. These interactions create gaps, waves, and spiral density structures that propagate through ring systems like cosmic music made visible. The mathematical precision of these patterns reveals the underlying harmony of gravitational forces operating on multiple scales simultaneously. The chemical differentiation that occurred during moon formation created the layered internal structures we infer from gravitational and magnetic field measurements. Heavy elements sank toward the centers while lighter materials rose to the surfaces, creating compositional gradients that influence everything from magnetic field generation to geological activity. This differentiation process transforms homogeneous mixtures of rock and ice into complex stratified worlds. The preservation of ancient terrains on many moons provides natural laboratories for studying processes that operated during the solar system's youth. These pristine surfaces preserve impact crater populations, chemical compositions, and geological features that have been erased from more active worlds. They serve as cosmic museums, maintaining records of conditions and events from billions of years ago. The organic compound synthesis occurring in the atmospheres and on the surfaces of outer system moons creates complex chemistry under conditions that might have existed on early Earth. The hydrocarbon haze particles raining down on Titan's surface, the radiation-processed organics coating Kuiper belt objects, and the complex molecules detected in the plumes of Enceladus all represent experiments in prebiotic chemistry occurring on cosmic scales. The extreme temperature variations we encounter throughout our journey, from the molten sulfur lakes of Io to the nitrogen ice plains of Pluto, demonstrate how the same basic materials can behave in radically different ways depending on environmental conditions. Water ice becomes as hard as granite in the outer solar system, while sulfur compounds remain liquid and dynamic, even at temperatures that would instantly freeze most other substances. The gravitational sculpting that shapes moon surfaces and interiors operates through mechanisms that continue to surprise us with their variety and complexity. From the linear ridges on Europa created by tidal stresses to the chaotic terrain on Miranda, possibly formed by catastrophic disruption and reassembly. These processes create geological features that have no terrestrial analogues, yet follow physical principles we can understand and model. The dust dynamics operating throughout moon systems reveal how even microscopic particles play crucial roles in larger evolutionary processes. Impacts eject material that feeds ring systems, creates tenuous atmospheres, and influences the orbits of larger objects through radiation pressure effects. This interconnectedness demonstrates that no component of a planetary system exists in isolation. The auroral phenomena we observe around magnetized moons create some of the most beautiful light displays in the solar system. These glowing footprints, painted in planetary atmospheres by electrical currents generated by moon magnetosphere interactions, serve as remote probes of moon properties, allowing us to study internal structures and atmospheric compositions from great distances. The evolutionary pathways that led to the current configurations of moon systems involved processes of incredible violence and complexity. Giant impacts shattered and reformed worlds. Gravitational captures flung objects across the solar system. Orbital migrations caused by planetary interactions reshuffled entire satellite systems. These chaotic processes somehow produce the stable, harmonious configurations we observe today. The thermal evolution of moons over geological time creates the diverse landscapes we encounter, from the geologically active surfaces of the largest satellites to the pristine, crater-saturated terrains of smaller objects. The interplay between initial heat from accretion, ongoing heating from radioactive decay and tidal forces, and heat loss through radiation to space determines whether a moon remains active or freezes into geological death. The magnetic field interactions between moons and their parent planets create complex current systems that flow through space over distances of millions of kilometers. These invisible electrical circuits carry energy and momentum between different components of planetary systems, influencing everything from auroral displays to the erosion of moon atmospheres by charged particle bombardment. The seasonal cycles operating on moons with eccentric orbits or around planets with tilted axes create climate variations that span human lifetimes or even centuries. These extreme seasonal changes drive atmospheric dynamics, surface processes, and possibly biological rhythms that operate on timescales completely foreign to terrestrial experience. The crystalline structures formed by water ice and other frozen compounds under the extreme pressures and temperatures found in moon interiors take forms that don't exist naturally on Earth. These exotic ice phases may flow like warm putty despite being solid, creating convective processes that transport heat and drive geological activity in ways we're only beginning to understand. The photochemical processes occurring in the tenuous atmospheres of many moons demonstrate how even trace amounts of atmospheric gases can support complex chemical reactions. Ultraviolet radiation cosmic rays and charged particles from planetary magnetospheres break apart simple molecules and reassemble them into more complex compounds, creating the organic hazes and surface deposits that give many moons their distinctive appearances. The impact crater populations preserved on ancient moon surfaces provide natural chronometers that allow us to date geological events and understand the bombardment history of the entire solar system. By comparing crater densities between different regions and different worlds, scientists can construct timelines of cosmic violence that shaped every solid surface we encounter. The subsurface ocean dynamics operating beneath ice gradients and heat shells involve complex interactions between tidal heating, chemical transport that may create environments more diverse than Earth's surface oceans. These hidden seas might contain multiple layers with different compositions, temperatures, and chemical properties, creating three-dimensional habitats of staggering complexity. The atmospheric chemistry occurring on moons with substantial gaseous envelopes involves processes that transform simple compounds into complex organic molecules through pathways that might have operated on early Earth. These natural chemical laboratories provide insights into how the molecular building blocks of life might form and evolve under a wide range of environmental conditions. The gravitational interactions between multiple moons in the same system create resonances and perturbations that can pump orbital eccentricity, maintain tidal heating, and prevent systems from settling into simple, stable configurations. These complex many-body dynamics ensure that moon systems remain active and interesting over geological timescales. As our unprecedented journey through every moon in our solar system reaches its conclusion, we find ourselves profoundly changed by the diversity and wonder we've witnessed. We've flown through worlds of fire and ice, ancient craters and active volcanism, hidden oceans and methane lakes, each one revealing new aspects of how gravity, chemistry, and time can shape matter into forms of incredible beauty and complexity. The more than 200 moons we've encountered represent just the beginning of our understanding of satellite systems throughout the universe. Every new discovery, every successful mission, every theoretical breakthrough adds new chapters to the ongoing story of these remarkable worlds. Our cosmic voyage has shown us that the universe is far richer, stranger, and more wonderful than we ever dared to imagine, and that the greatest adventures in exploration may still lie ahead of us, waiting among the moons of distant stars. The technological achievements that brought us this far represent some of humanity's greatest triumphs. Every spacecraft that has ventured into the outer darkness, every instrument that has measured magnetic fields around distant worlds, every camera that has captured images of alien landscapes has expanded our understanding of what's possible in the cosmos. These robotic explorers serve as our eyes and hands in places where no human could survive, transmitting back data that transforms our perspective on existence itself. But our journey has revealed something even more profound than individual discoveries. We've witnessed the incredible interconnectedness that binds every object in our solar system into a single, unified whole. The materials blasted from Io's volcanoes eventually find their way into Jupiter's magnetosphere. The organic compounds synthesized in Titan's atmosphere rain down to create landscapes of alien beauty. The gravitational resonances that control moon orbits ripple outward to influence ring systems millions of kilometers away. This interconnectedness extends beyond individual planetary systems to encompass our entire cosmic neighborhood. The same impact events that created Earth's moon also scattered debris throughout the inner solar system. The migration of giant planets early in solar system history reshaped satellite systems and sent objects careening between the inner and outer regions. Every moon we've visited bears the signature of processes that operated on a scale spanning our entire solar system. The diversity of environments we've encountered challenges every assumption about where interesting processes can occur. From the radiation-bombarded surfaces around Jupiter to the perpetual twilight of the Kuiper Belt, from the crushing pressures deep within ice shells to the near-vacuum conditions on airless worlds, complex chemistry and dynamic geology operate under conditions that would have seemed impossible just decades ago. Perhaps most remarkably, our cosmic voyage has revealed that activity and change aren't limited to worlds near stars. Tidal heating can maintain liquid oceans for billions of years, even in the frozen outer reaches of planetary systems. Radioactive decay provides steady energy sources that operate independently of stellar heating. Chemical reactions driven by cosmic radiation can synthesize complex organic molecules in the coldest, most isolated environments imaginable. The implications extend far beyond our own solar system. If worlds as diverse as Europa, Enceladus, and Titan can harbor potentially habitable environments around a single star, then the cosmos must contain countless variations on these themes. The discoveries we've made suggest that interesting chemistry, active geology, and possibly even life might be far more common throughout the universe than we ever imagined. The mathematical precision underlying everything we've observed reveals a universe governed by elegant physical laws that operate with clockwork precision across vast scales of space and time. The orbital resonances that create stability in moon systems, the tidal forces that generate internal heating, the gravitational interactions that sculpt ring structures, all demonstrate that chaos and order coexist in perfect balance throughout the cosmos. Our exploration has also revealed the incredible patience required to understand these distant worlds. The seasonal cycles on some moons span human lifetimes. The geological processes that shape their surfaces operate over millions or billions of years. The evolution of their atmospheres and interiors unfolds on timescales that dwarf human history. Yet through careful observation and theoretical modeling, we've learned to read the stories these worlds tell about their ancient past and ongoing evolution. The organic chemistry occurring throughout the outer solar system provides a natural laboratory for studying the chemical processes that might have preceded life on Earth. The complex hydrocarbons raining from Titan's skies, the organic compounds detected in Enceladus's geysers, and the radiation-processed materials coating countless small moons all represent experiments in prebiotic chemistry occurring on cosmic scales. The subsurface oceans we've discovered represent some of the most stable environments in the solar system. Protected from the harsh radiation of space by kilometers of ice, warmed by tidal heating that can persist for billions of years, and possibly enriched with dissolved minerals from rocky cores, these hidden seas might provide havens for life that could outlast the surface oceans of planets orbiting within stellar habitable zones. The magnetic field phenomena we've encountered reveal the complex electrical systems that operate throughout planetary magnetospheres. Currents flowing between moons and planets carry energy across millions of kilometers of space, creating auroral displays that paint glowing footprints in atmospheric gases and generating electromagnetic effects that influence everything from particle acceleration to atmospheric erosion. The impact processes that have shaped every solid surface we visited tell stories of cosmic violence that continue to influence solar system evolution today. The late heavy bombardment left its signature on worlds throughout our cosmic neighborhood, while ongoing impacts continue to resurface some moons, while preserving ancient terrains on others. These collision events serve as both destructive and creative forces, erasing old landscapes while creating new geological features. The atmospheric dynamics operating on moons with substantial gaseous envelopes create weather systems that rival anything seen on planets. Titan's methane cycle generates, and seasonal clouds, precipitation changes that mirror Earth's hydrological processes, but operate with completely different chemistry. The thin atmospheres of distant moons undergo dramatic variations as their elliptical orbits carry them closer to and farther from the sun's faint warmth. The cryovolcanic processes we've witnessed represent some of the most spectacular geological phenomena in the solar system. These eruptions of water, ammonia, and other volatile compounds create features that have no terrestrial analogues, yet they follow the same basic physical principles that drive volcanic activity everywhere. The geysers shooting from Enceladus's south pole provide direct samples of a subsurface ocean, while the nitrogen plumes on Triton demonstrate that geological activity can persist even in the solar system's frozen frontier. The binary relationships between some moons create gravitational dynamics so complex they push our computational models to their limits. These paired worlds, orbiting around common centers of mass while simultaneously circling their parent planets, exist in delicate gravitational balance that somehow persists for billions of years. Their existence demonstrates that stable orbital configurations can take forms far more exotic than simple elliptical paths around bodies. The ring-moon interactions central we've observed throughout the gas giant systems reveal how solid objects can control the behavior of countless individual particles through gravitational shepherding. These interactions create gaps, waves, and spiral structures that propagate through ring systems like frozen mathematical beauty music, demonstrating the underlying celestial mechanics. The preservation of ancient materials on many moon surfaces provides natural archives of solar system history. These pristine terrains maintain records of bombardment events, atmospheric compositions, and chemical processes that occurred billions of years ago. They serve as cosmic time capsules, preserving information about conditions during the solar system's violent youth that has been erased from more geologically active worlds. The chemical differentiation that occurred during moon formation created the complex internal structures we infer from gravitational and magnetic measurements. The separation of heavy and light elements during accretion produced layered compositions that continue to influence geological processes billions of years later. These internal architectures determine everything from magnetic field generation to the persistence of subsurface oceans. The thermal evolution pathways that different moons have followed create the diverse landscapes we observe today. Size, composition, and orbital environment all influence how quickly worlds lose their primordial heat and whether they can maintain geological activity over cosmic time. The largest satellites retain enough internal energy to drive active processes, while smaller objects freeze into the configurations they achieved early in their histories. The radiation environment surrounding the giant planets creates some of the most extreme conditions in the solar system. Charged particles accelerated to incredible energies by planetary magnetic fields continuously bombard moon surfaces, driving chemical reactions that transform simple compounds into complex organic molecules. These natural particle accelerators operate continuously, creating chemistry that might be impossible under calmer conditions. The dust production and transport processes operating throughout moon systems create invisible connections between distant objects. Micrometeorite impacts eject material from moon surfaces that can travel vast distances before settling onto other worlds or being swept up by ring systems. This continuous exchange of materials creates chemical mixing on scales that span entire planetary systems. The escape processes that remove atmospheric gases from moons operate through various mechanisms that depend on factors like gravity, temperature, and magnetic field strength. From thermal escape driven by solar heating to sputtering caused by energetic particle bombardment, these processes demonstrate that atmospheres are dynamic systems that can evolve dramatically over geological time. The seasonal variations experienced by moons in eccentric orbits or around planets with tilted rotation axes create climate cycles that operate on timescales completely foreign to terrestrial experience. These extreme seasonal changes can span decades or centuries, driving atmospheric and surface processes that challenge our understanding of how weather and climate systems can operate. The exotic ice phases that form under the extreme pressures found deep within large icy moons create materials with properties unlike anything we encounter on Earth. These high-pressure ices may flow like warm plastic despite being solid, enabling convective processes that transport heat and drive geological activity through mechanisms we're only beginning to understand. The photochemical reactions occurring in the tenuous atmospheres of many moons demonstrate how complex chemistry can proceed even under conditions of near vacuum. Ultraviolet radiation and energetic particles break apart simple molecules and reassemble them into more complex compounds, creating the organic hazes and surface coatings that give many outer system moons their distinctive colors and compositions. The gravitational resonances that control the orbits of multiple moons in the same system create mathematical relationships so precise they seem almost orchestrated. These orbital harmonies, where satellites complete their circuits in exact ratios to one another, provide stability that allows complex moon systems to persist for billions of years without flying apart or colliding. The magnetic field interactions between moons and their parent planets generate electrical currents that flow through space over distances measured in planetary radii. These cosmic electrical circuits carry energy and momentum between different components of planetary systems, influencing processes ranging from auroral displays to the gradual erosion of moon atmospheres. The impact crater populations preserved on ancient surfaces provide natural chronometers that allow us to date geological events and understand the bombardment history of the entire solar system. By comparing crater densities between different terrains and different worlds, scientists can construct detailed timelines of the cosmic violence that shaped every solid surface we've encountered. The subsurface ocean dynamics operating beneath ice shells involve complex three-dimensional circulation patterns driven by tidal heating, chemical gradients, and temperature variations. These hidden seas might contain multiple layers with different compositions and properties, creating environments more diverse and complex than Earth's surface oceans. As our unprecedented journey through every moon in our solar system draws toward its final conclusion, we find ourselves forever changed by the incredible diversity and beauty we've witnessed. From the sulfur-painted landscapes of Io to the methane lakes of Titan, from the ancient scars of Callisto to the active geysers of Enceladus, each world has revealed new aspects of how matter and energy can combine to create wonders beyond imagination. The technological achievements that made this cosmic voyage possible represent humanity at its finest. Every successful spacecraft mission, every innovative instrument design, every mathematical model that helps us understand complex gravitational interactions demonstrates our species' remarkable ability to extend our senses and comprehension far beyond the limitations of our earthbound origins. The implications of our discoveries reach far beyond academic curiosity. The subsurface oceans we've found may harbor life forms unlike anything on Earth. The organic chemistry laboratories operating throughout the outer solar system provide insights into the chemical pathways that might have led to biology on our own world billions of years ago. The diverse environments we have explored expand our understanding of where life might exist throughout the cosmos. The mathematical beauty underlying everything we've observed reveals a universe governed by elegant physical laws that create order from apparent chaos. The precise orbital relationships, the complex resonances, the delicate gravitational balances all demonstrate that the cosmos operates according to principles we can understand and appreciate through careful observation and theoretical analysis. Our cosmic odyssey has also revealed the incredible interconnectedness that binds every component of our solar system into a unified whole. Materials launched from one world can eventually reach others. Gravitational interactions between distant objects influence the evolution of entire systems. The history of each moon we've visited reflects processes that operated on scales spanning our entire cosmic neighborhood. The future exploration of these remarkable worlds promises discoveries that will continue to transform our understanding of planetary science, astrobiology, and our place in the universe. Missions currently being planned will drill through ice shelves to sample hidden oceans, search for signs of past or present life, and explore the surfaces of moons where no spacecraft has ever landed. The diversity of processes we've witnessed operating under extreme conditions suggests that interesting chemistry, active geology, and possibly even life might be far more common throughout the universe than we ever imagined. If a single star system can produce such an astounding variety of worlds, then the cosmos must contain countless variations on these themes, each one a unique experiment in planetary evolution. Our journey has shown us that exploration is fundamentally about expanding our perspective on what's possible. Every moon we've visited has challenged our preconceptions and forced us to think more broadly about the nature of worlds and the processes that shape them. The universe has proven to be far stranger, more beautiful, and more wonderful than our wildest scientific imagination could have conceived. The story of these moons continues to unfold with every new observation, every successful mission, and every theoretical breakthrough that helps us better understand these distant worlds. Our unprecedented flight through every satellite in our solar system has revealed that we live in a cosmos of incredible richness and complexity, where wonders await discovery wherever we have the curiosity and courage to look. As we finally return from this extraordinary voyage through our solar system's family of moons, we carry with us a profound appreciation for the cosmic processes that have shaped these worlds and continue to drive their evolution. We've learned that the universe is not just vast and ancient, but also dynamic and creative, constantly generating new forms of beauty and complexity through the patient operation of physical laws over cosmic time. The more than 200 moons we've encountered represent just the beginning of our understanding of satellite systems throughout the cosmos. Each successful mission, each new discovery, each theoretical insight adds another piece to the grand puzzle of how planetary systems form, evolve, and potentially harbor life. Our cosmic adventure has shown us that the greatest discoveries may still lie ahead, waiting among the moons of distant stars, ready to reveal new chapters in the ongoing story of our universe's incredible creativity and endless capacity for wonder. The gravitational choreography we've witnessed throughout our solar system reveals itself most dramatically in the realm beyond Neptune, where the fundamental forces that govern celestial mechanics operate at their most extreme limits. Here, in the twilight zone, where our sun's influence begins to fade into the cosmic background, we encounter moon systems that push the very definition of what constitutes a gravitationally bound pair. The Kuiper Belt objects we've explored demonstrate that even the smallest worlds can maintain companions through gravitational bonds so tenuous they seem almost miraculous. These binary systems, where objects separated by mere kilometers orbit their common center of mass over periods measured in days or weeks exist in a delicate balance that could be disrupted by the slightest external perturbation. Yet somehow they persist, dancing their ancient orbital waltz in the perpetual twilight of the outer solar system. The chemical processes we've observed operating in these frozen realms reveal how complex molecular evolution can occur even at temperatures that would instantly solidify most substances we encounter on Earth. The organic compounds coating these distant worlds result from billions of years of cosmic bombardment, slowly transforming simple hydrocarbons into increasingly complex molecules through pathways that might mirror the prebiotic chemistry that preceded life on our own planet. The impact velocities in these distant regions operate under completely different physical regimes than anything we observe in the inner solar system. Objects moving at relative speeds measured in hundreds of meters per second, rather than kilometers per second, create collision dynamics that tend to result in accretion rather than catastrophic disruption. These gentle impacts may explain how some of the binary systems we've encountered manage to form and persist despite the chaotic environment of the early solar system. The thermal processes operating on these distant moons demonstrate how even trace geological activity over amounts of internal heat can drive cosmic timescales. Radioactive decay of long-lived isotopes provides steady energy input that can maintain subsurface liquids even at distances where solar heating becomes negligible. These internal heat sources operate independently of stellar proximity, suggesting that habitable environments might exist throughout the galaxy in locations we're only beginning to consider. The atmospheric dynamics on moons with substantial gaseous envelopes reveal how complex meteorological systems can develop and persist under conditions of extreme cold and low atmospheric pressure. The seasonal cycles we've observed, driven by orbital eccentricity and planetary obliquity, create climate variations that span human lifetimes while following physical principles that mirror terrestrial weather patterns but operate with completely different chemistry. The magnetic field phenomena we've encountered throughout our journey provide windows into the internal structures and dynamics of these distant worlds. The interaction between planetary magnetic fields and moon magnetospheres creates electrical systems that span millions of kilometers, generating currents that influence everything from auroral displays to the gradual erosion of atmospheric components through charged particle interactions. The ring systems we've discovered around multiple objects reveal that these elegant structures aren't limited to the gas giants, but can form wherever the right combination of gravitational forces and debris sources coincide. The tenuous rings around some moons, composed of dust particles ejected by micrometeorite impacts, demonstrate how even the smallest worlds can create and maintain these beautiful celestial ornaments through ongoing geological processes. The evolutionary pathways that led to the current configurations we observe involved processes of incredible complexity and violence. The giant impacts that shattered and reformed worlds, the gravitational captures that brought distant objects into orbital embrace, and the tidal interactions that gradually synchronized rotations and orbital periods all contributed to creating the harmonious systems we explore today. The dust dynamics operating throughout these distant regions create invisible connections between objects separated by vast distances. Particles ejected from one world by impact events can travel for years or decades before settling onto other surfaces, creating a slow but steady exchange of materials that gradually homogenizes compositions across entire regions of space. The cryovolcanic processes we've witnessed represent some of the most spectacular geological phenomena in the solar system, demonstrating how internal pressures can overcome the gravitational binding of small worlds to eject materials hundreds of kilometers into space. These eruptions of volatile compounds create surface features and atmospheric phenomena that have no terrestrial analogues, yet follow the same basic physical principles that govern all volcanic activity. The photochemical reactions occurring in the tenuous atmospheres of these distant worlds show how complex organic synthesis can proceed under conditions of near vacuum and extreme cold. Ultraviolet radiation from distant stars, cosmic ray bombardment, and charged particle interactions all contribute to breaking apart simple molecules and reassembling them into increasingly complex compounds over geological timescales. The seasonal variations experienced by objects in highly eccentric orbits create climate cycles of extraordinary duration and intensity. Imagine seasons where summer and winter are separated by centuries, where atmospheric composition changes dramatically as orbital distance varies by factors of 2 or more, where entire atmospheric systems can freeze out and sublime back into existence over the course of a single orbital period. The preservation of ancient materials on surfaces throughout the outer solar system provides natural archives of solar system history, stretching back to the earliest epochs of planetary formation. These pristine terrains maintain chemical and isotopic signatures of processes that operated during the solar nebula phase, offering glimpses into conditions that existed before planets had fully formed. The resonance relationships governing the motions of multiple objects in complex gravitational systems create mathematical harmonies of incredible precision. These orbital relationships, where periods of revolution maintain exact integer ratios over billions of years, demonstrate how gravitational forces can create stability and predictability, even in systems that appear chaotically complex. The thermal evolution of these distant worlds follows pathways determined by their initial compositions, sizes, and orbital environments. The interplay between primordial heat from accretion, ongoing heating from radioactive decay, and heat loss through radiation to space determines whether objects remain geologically active or freeze into the configurations they achieved early in their histories. The binary formation mechanisms that created many of the paired objects we've encountered probably involved gentle collisions during the solar system's formation epoch, when relative velocities were low enough to allow accretion rather than catastrophic disruption. These formation events created gravitationally bound systems that have persisted for over 4 billion years, despite the chaotic environment of the early solar system. The atmospheric escape processes operating on these distant worlds demonstrate how tenuous gaseous envelopes can persist over cosmic timescales, when gravitational binding is sufficient to retain atmospheric components against thermal escape and solar wind erosion. The balance between atmospheric loss and replenishment through sublimation or outgassing determines whether objects can maintain detectable atmospheres over geological time. The chemical differentiation that occurred in the largest objects during their formation created internal structures with distinct compositional layers that continue to influence geological processes billions of years later. The separation of rocky and icy components during accretion produced cores and mantles with different physical properties, enabling convective processes and magnetic field generation in objects that might otherwise remain geologically inert. The impact crater populations preserved on ancient surfaces provide detailed records of the bombardment history throughout different regions of the solar system. The size-frequency distributions of craters on various worlds reveal how impact rates have changed over cosmic time, and how the populations of impacting objects varied between different regions of the early solar system. The exotic ice phases that form under the pressure and temperature conditions found in the interiors of large icy objects create materials with properties unlike anything we encounter under terrestrial conditions. These high-pressure ice polymorphs may flow like viscous liquids despite being crystalline solids, enabling convective heat transport and geological activity through mechanisms we're only beginning to understand. The radiation processing of surface materials throughout the outer solar system creates complex organic chemistry through pathways that operate over millions or billions of years. Cosmic ray bombardment gradually transforms simple hydrocarbons into increasingly complex molecules, creating the dark, reddish materials that coat many outer solar system objects and may represent significant reservoirs of organic compounds. The gravitational interactions between objects in complex multiple body systems create orbital dynamics so intricate they require sophisticated numerical methods to model accurately. These systems exist in states of delicate gravitational balance, where the slightest perturbation could disrupt stable configurations that have persisted since the solar system's formation. The magnetic field interactions between electrically conducting objects and the charged particle environments of their host systems generate electromagnetic phenomena that influence atmospheric evolution, surface chemistry, and the overall energetic balance of these distant worlds. These processes create invisible connections spanning vast distances while driving chemical and physical changes that continue to reshape these ancient surfaces. The subsurface ocean dynamics that may operate beneath the ice shells of some distant objects involve complex circulation patterns driven by tidal heating, chemical gradients, and rotational effects. These hidden seas, if they exist, might represent some of the most stable aqueous environments in the solar system, protected from surface temperature variations and potentially maintaining liquid conditions for billions of years. The atmospheric chemistry occurring in the gaseous envelopes of objects with substantial atmospheres involves photochemical and radiochemical processes that create complex organic molecules through pathways that might have operated on early Earth. These natural laboratories for prebiotic chemistry provide insights into how blocks of life might form the molecular building and evolve under a wide range of environmental conditions. The seasonal atmospheric dynamics driven by orbital eccentricity and obliquity create weather systems that operate on timescales completely foreign to terrestrial experience. These climate cycles, spanning decades or centuries, drive atmospheric transport processes, surface atmosphere interactions, and potentially biological rhythms that challenge our understanding of how planetary atmospheres can behave. The dust production mechanisms operating throughout these distant regions involve impact processes, sublimation events, and electromagnetic effects that continuously modify surface compositions and create tenuous particle environments around many objects. This ongoing dust production provides raw material for ring systems while also influencing the optical properties and thermal behavior of object surfaces. The chemical evolution pathways followed by organic compounds in radiation-rich environments demonstrate how complex molecular synthesis can occur through non-biological processes over cosmic timescales. The gradual transformation of simple hydrocarbons into complex organic polymers through radiolysis creates materials that might preserve chemical information about early solar system conditions. The gravitational focusing effects that concentrate impact projectiles towards certain regions of object surfaces create non-uniform crater distributions that reveal information about the dynamics of impactor populations throughout solar system history. These focusing mechanisms help explain why some surfaces show higher crater densities than others, despite experiencing similar bombardment environments. The thermal cycling effects caused by rotation and orbital motion drive, expansion, and contraction processes that can fracture surface materials and create complex geological features, even on objects too small to maintain significant internal heat sources. These thermally driven processes demonstrate how even modest temperature variations can sculpt landscapes over geological time. The electromagnetic interactions between charged dust particles and magnetic field environments create complex plasma physics phenomena that influence dust dynamics, atmospheric chemistry, and surface charging effects throughout the outer solar system. These processes operate continuously but subtly, gradually modifying the properties of dust and gas populations over cosmic timescales. The orbital migration processes that occurred during the early solar system's dynamical evolution reshape satellite systems throughout the outer regions, creating the current configurations we observe today. These migration events, driven by gravitational interactions during planetary formation, explain many of the unusual orbital characteristics we encounter among irregular satellites and captured objects. The compositional gradients preserved in differentiated objects provide records of the thermal and chemical conditions that existed during accretion and early evolution. These internal structures, revealed through gravitational and magnetic field measurements, tell stories of heating events, chemical segregation, and cooling processes that shaped these worlds during their formative epochs. The atmospheric photochemistry operating under the low light conditions of the outer solar system demonstrates how complex chemical networks can function using minimal energy inputs from distant stellar radiation. These photes, by cosmic chemical processes, supplement ray interactions, and charged particle bombardment, create and maintain atmospheric compositions that continue to evolve over geological time. As our extraordinary journey through every moon in our solar system approaches its final moments, we find ourselves profoundly transformed by the cosmic perspective we've gained. We've witnessed processes operating under conditions so extreme, they challenge our understanding of what's possible in nature, yet following physical principles so elegant, they reveal the underlying mathematical beauty of the universe itself. And so we return from this unprecedented odyssey through every moon in our solar system, forever changed by the wonders we've encountered. From the volcanic fury painting Io's surface in brilliant sulfur to the hidden oceans beneath Europa's ice, from Titan's methane lakes to the nitrogen geysers piercing Triton's frozen darkness, we've witnessed a cosmic diversity that defies imagination. These aren't just distant rocks orbiting planets. They're entire worlds, each conducting its own unique experiment in chemistry, geology, and perhaps even biology. Our journey has revealed that in this vast universe of ours, wonder and mystery exist wherever we dare to look. I hope you had an amazing time with me here at Boring Science. I will see you tomorrow as always. Until then, stay curious, keep wondering. This is Boring Science signing off. Cheers.